Hello everyone. I'm going to introduce the paper Designing Truthful Spectrum Auctions for Multi-Hop Secondary Networks. I'm going to start the presentation. Uh, I'm going to introduce secondary spectrum auction. Wireless communications crucially rely on the availability of bandwidth spectrum, so spectrum allocation is one of the most important subjects. But traditional allocation is too static, which is prone to inefficient, so there remains large amount of idle spectrum channels, while new users are unable to access them. In a secondary spectrum market, a spectrum owner or primary user leases its idle spectrum channels to secondary users through auctions. Secondary users submit bids for channels and pay the primary user a price to access the channel if their bids are successful. Second, I'm going to introduce multi-hop routing. When network coverage area is large enough to cover multiple nodes, a node can use another node as relays. This type of communication is called multi-hop routing. Multi-hop routing can be more energy efficient than single-hop routing because long-distance transmission requires much more power. Third, I'm going to introduce truthful auction. In truthful auctions, the best strategy of bidders is bidding his/her true valuation, so they have no incentive to lie. Truthful auction simplifies decision-making at secondary users and lays a foundation for good decision-making at primary user because he can easily predict the strategy of bidders. Therefore, this paper designs truthful auction for a foundation of reaching social welfare maximization, maximizing the aggregated happiness of everyone in the system. I'm going to introduce the system modeling of this paper. First, its auction design. WI denotes the valuation of each agent I. BI denotes the bidding of each agent I, and B minus I is the bidding vector of all the bids except I. PI denotes the actual payment of agent if he wins. UBI, B minus I is the utility of I. Then UBI, minus BI is its valuation minus payment if he wins. Conditions for truthful action. When an auction is truthful, we have UI. Its valuation bidding is the best strategy. There is a theorem by Meyerson conditioning an auction to be truthful. Mm, The probability of winning is monotonically non-decreasing in its bidding, and agent I bidding BI is the payment is like this. Uh, When especially when an auction is deterministic, then P is 0 or 1 by theorem, then this area will be the payment of the agent. In this case, the critical bidding must the second price. The winner must pay the second price of the bidding because if one is winning, then critical bidding must be its second price among the biddings. This case is called the second price auction or the Bickery auction. Yeah, I'm going to introduce the exact auction model in this paper. Each secondary network participates as agents and primary network as the auctioneer. Every networks in the system are expressed as a graph, and secondary networks demands for multi-hop transmission from source to destination, which can be expressed as a graphical path. Every edges in secondary networks can use one of the channels of primary network, And intersecting edges from different secondary networks cannot use the same channel because of interference. Before the auction starts, each secondary network I submits the auctioneer a compound bid, including his network graph, source, destination, and bidding. Then the auctioneer computes conflict graph where secondary networks will compete for their channel. In auction model, mm, we can denote GI, the network graph, edges, vertices of agent I respectively, and SI, DI are the source and destination nodes of agent I. H is the conflict graph and edges and vertices respectively, and L is a link between nodes U and V in the network graph of agent I. And X is a binary variable denoting whether channel C is assigned to L. If X is 1, then we can say the channel C is assigned to this L. And F is a flow rate between nodes UV in the network graph of agent I. Gamma is a sublinear function denoting the valuation of agent I on a solution f, x. And the utility of agent is this phi. And and I'll introduce the objectives and constraints in this system. Objective function X is maximizing the whole utility summation. And channel interference constraints says if two edges are in conflict, then at most one allocation can be done. And flow conservation constraints says the summation of inner flow and summation of outgoing flow are same. And capacity constraints says the flow can be made the if there is an allocation of channel. And utility constraint says the utility is not no more than the valuation of this. And I'll introduce the greedy channel allocation algorithm. We first get compound bids from all the secondary networks and compute the conflict graph. And for each agent, we calculate his uh, his all the sum of his sum of number of his conflict his conflicting secondary networks, and we divide his bidding by the summation of his conflicting networks. Then we allocate in order of this phi instead of just bi to prevent severe interference. And now we see the example, and when phi A is the most, and then phi B, phi C, phi D. First, in the figure A, we can see that the first phi can be allocated by channel 1, and then we can allocate channel B by allocating channel 2 in this conflict graph. And now C cannot be allocated any channel because in this situation, channel 1 and channel 2 are all allocated by other secondary networks. So C cannot be allocated by any channels. And now D can be allocated by this. And I'll introduce a payment calculation algorithm. To make algorithm to be truthful, the payment must be critical bidding by theorem 1. critical bidding of I is the highest bidding among those who lost to I. To get this value, the algorithm 2 assumes the winner's bid to be 0 and calculate the new winner's bid in that assumed situation. And last, I introduce a randomized auction algorithm. The algorithm 3 uses Vickery-Clark-Groves auction, which assigns the items in a social optimal manner. The plugin algorithm A solves the LPR problem by using any general LP solution technique. The plugin algorithm B solves the optimization problem, which is classic multi-hop, multi-channel wireless routing problem, through several known algorithms. This is the simulation results of the paper by auction efficiency. In the simulation, all bids are taken from a uniform distribution, and every nodes are randomly distributed in bounded Euclidean surface. The paper evaluates its performance in terms of auction efficiency, which reflects the portion of secondary networks demand that are satisfied, weighted by valuation factor, like this. The simulation varied the number of channels, secondary networks, and approaches. We can easily see that if we increase the number of channels, then the auction efficiency increases. And if we increase the number of secondary networks, then auction efficiency decreases. And our proposed multi-channel enabled auction model is even better than the already existing multi-item auction method. And the second simulation result is comparison with the knife greedy algorithm and the proposed algorithm. The paper compares the performance of auctions between knife greedy one and the one proposed in the paper. Three performance was considered: spectrum utilization, user satisfaction, and social welfare, while varying the number of secondary networks. The proposed one outperforms the naive B algorithm, but differences are not large. In conclusion, the paper proposed the concept of secondary network, relaxing the oversimplifying assumption on secondary users in existing research. The first proposed auction is simple, greedy-style deterministic auction that heuristically maximizes social welfare with its truthfulness. The second one is randomized auction, linear optimization-based auction that is not only truthful but also provides proven guarantees on social welfare. The further work will improve the performance guarantee of the randomized auction by proving a tighter bound on social welfare approximation. Thank you for your listening, and any questions or suggestion will be very helpful. Thank you very much.